We've been talking a lot about solutions, about things dissolved, especially in water, and we would be remiss if we didn't have a discussion as to how chemists talk about the concentration of solute. And as an example of that, let's say you had some sugar water, all right? Well, your sugar water could have just a little bit of sugar in it, or it could have a lot of sugar in it. If you didn't have a lot of sugar, it would be hard to taste and stuff. You wouldn't taste it very well. On the other hand, if you had too much sugar, it would be kind of, so sweet you couldn't stand it, right? So anyway, this is a really important part in chemistry. The concentration is going to tell us like how much of the solute, the exciting thing, is being delivered. And the concentration is usually a reflection, as we're going to see, in terms of how many moles are being given. So instead of talking about not so sweet and very sweet, we could say, well, there were only 0.1 moles or something versus 5 moles of sugar being delivered, and that's a big deal. So in chemistry, most of the time, we use for concentration a unit called molarity. And molarity, which is given this symbol capital M, means moles of solute per liters of solution. So as an example, if you saw a solution that was labeled 3.6 M, that means 3.6 molarity, or 3.6 is going to be the concentration. And the 3.6 would be 3.6 moles of solute per liter of solution. And molarity is a very important unit. It's used extensively with acids and bases, and we're going to see it makes making things a lot easier. But just realize that if you see this capital M, that's molarity. And you should not, of course, use capital M now for anything but molarity. So if you've been using a capital M for moles, all right, stop it. Or if you've been using capital M for molar mass, all right, please don't, because big M, moles per liter. Once in a while, you'll see numbers that are in square brackets like that, and that means molarity too. That's not as common, but if you do see it, just remember that.
To prepare a solution of known concentration, we must first weigh the solute. We need an accurate volumetric flask designed to hold 250 milliliters. We first add the solute to the empty flask. The flask is filled about halfway with water and mixed to dissolve the solute. We add water in stages. Combining all the solvent with the undissolved solute in one step can lead to inaccurate measurements. We mix again. The solution is prepared.
This is an example of how you can calculate molarity. Now remember that molarity, big M, is moles of solute per liter of solution. And in this problem, our solute is not like sugar. Darn it. No, I'm just joking. Sugar is, of course, weird for you. Anyway, the solute, the exciting part for chemists anyway, is nickel-2 chloride hexahydrate, NiCl2.6H2O. This is a hydrated compound. And the solvent is water. And nickel-2 chloride has a chloride in it. Chloride is almost always soluble, AQ, unless it's with silver, mercury, or lead. Nickel is not silver, mercury, or lead, so this is going to dissolve really well. And it makes that kind of cool green color in the solution. It's really neat looking, but I digress. Let's say that we add 5 grams of nickel-2 chloride hexahydrate to enough water to make 250 milliliters of solution. We can use this information to calculate the molarity. Notice that they filled it up to that little line on the volumetric flask, that piece of glassware. That means you add enough water to make 250 milliliters of solution. The total volume, if you will, is 250. And most of that will be from water, but there, of course, will be a little solute as well. To do these kind of problems, you've got to have moles of solute and liters of solution. So let's turn the 5 grams of nickel-2 chloride hexahydrate into moles. So if you add up a nickel and 2 Cl's and 6 waters, you should get a molar mass of about 237.7 grams per mole. So turning 5 grams into moles, 3 sig figs, 0.0210 moles nickel-2 chloride hexahydrate. Now, molarity will be that number, the moles, divided by the liters. How many milliliters in a liter? If you said 1,000, well done. This is going to be an important thing. There's 1,000 milliliters in a liter. So 250 milliliters, notice it's 3 sig figs, 250 with a dot. We need to turn that into liters. So we'll divide by 1,000. 250 divided by 1,000 is 0.250 liters. So the moles of the nickel 2 chloride we calculated earlier divided by the volume in liters. 250 divided by 1,000 is 0.250. This comes out to be 0.0841 molar, or 0.0841 is the molarity. Down here on the bottom is an example of the square bracket version that sometimes you see with solutions. It means the same thing, all right? It just means the concentration of the nickel 2 chloride hexahydrate, 0.0841 molar, just like the other one does. Easy peasy, no problem. One interesting thing that happens when species dissolve in water is that the stoichiometry will be affected by the formula. And let me show you what I mean by that. This is an example of copper 2 chloride. And copper 2 chloride, very water soluble. Again, chloride is only insoluble with silver, mercury, and lead, and copper is not that one. However, because the formula is CuCl₂, you're going to end up, when it dissolves, with copper 2 plus ions and 2 chloride ions. So remember that in the back of your mind. Now, if we had a copper 2 chloride solution, which was 0.30 molar, or 0.30 moles per liter, then the copper 2 plus concentration would also be 0.30 moles per liter. 1 copper 2 chloride made 1 copper 2 plus ion. So 1 to 1, no big deal. But notice how the chloride is twice the concentration, and that's because there's a 2 right there. You get 2 moles of chloride for every 1 mole of copper 2 chloride that dissociates. So the chloride will be twice the concentration, 2 times 0.30 or 0.60 moles per liter. This can be kind of interesting because if you're trying to watch the chloride concentration and you're like, oh, this is only 0.30, whoops, so you put this in, and because of the stoichiometry, the CuCl₂, the 2 in that formula, you actually end up with twice the concentration. So chemists beware. This is an example where you have a barium chloride solution, and the barium chloride is 0.12 molar. And the question is, what are the ion concentrations in this solution? So first of all, we have to figure out what the barium chloride will break into. Now, barium chloride is ionic. It's got positives and negatives to it. And barium, a group 2A metal, will be positive 2 as an ion. And chloride, which is Cl-, notice there's a 2 right there. So just like the copper 2 chloride, the chloride is going to be different than the barium. Now, barium chloride, if you want, write it out. BaCl2 is going to break up into barium 2 plus and 2 Cl-. So if we have 0.12 molar barium chloride, the barium chloride to barium ratio, 1 to 1, this will also be 0.12 molar. However, you can probably see the chloride is going to be twice the barium chloride, 2 moles of Cl- for every 1 mole BaCl2. So 0.12 times 2, 0.24 moles per liter. And that's why the answer here would be C, all right? It's not 1 to 1, which would be answer A. It's not 1 to 1/2, which would be answer B. D, I don't know what they were smoking on that one, let's be honest. And then finally, E, Cl2, chlorine is a diatomic. Have no fear of ice clear, brew, but this is not chlorine. This is chloride. When chlorine combines with a metal, it becomes Cl-, chloride. And as chloride, you can have any combination of Cl's with a metal that you want. You could have NaCl, or in this case, BaCl2, or AlCl3, etc., etc. You only use the Cl2 when it's raw, when it's the elemental form. And this is not elemental chlorine. This is chloride. So we wouldn't have any Cl2. Cl2 would be 0. And as we talked about, chloride would be twice, or 0.24 molar. Using molarity is actually really handy and something the chemist does a lot. So let's say that we wanted to know the mass of oxalic acid, and oxalic acid is H2C2O4. How much of that in grams is required to make 250 milliliters of a 0.0500 molar solution? Now, believe it or not, oxalic acid is something you can buy at hardware stores and stuff like that. So let's say you wanted to make 250 milliliters of this 0.050 molar solution. The question is, how much do you need? Now, the way to solve this is to remember that big M is moles over liters. And if your volume V is in liters, then moles divided by liters times liters is like molarity times volume. So as long as your volume is liters, all right, you can multiply the molarity by the volume in liters to find the moles. And from the moles, you can use molar mass to find grams. So in this problem, what I would do, again, turning the milliliters into liters by dividing by 1,000. You're going to do that a lot in this section. So 0.0500 molar times 0.250 liters. The liters on the bottom here cancels the liters on the top. You're going to have 0.0125 moles now of oxalic acid. There's no more volume terms. The volume terms have been canceled. And oxalic acid, if you figure out the molar mass, it's 90.00 grams per mole. So multiply that by the 0.0125 moles we calculated earlier, 1.13 grams. So if on a balance you measured out 1.13 grams of oxalic acid and you filled it up in a volumetric flask or whatever to 250 milliliters of solution, you would have a 0.0500 molar concentration. And that's kind of a cool thing as a chemist.